Hey Sci Sisters! This is gonna be our first physics video. Woo woo! All our physics videos are going to be following the AP Physics C curriculum. C for crazy, because why are you taking this class? But anyways, initially I was thinking of starting with E&M and like circuitry and induction, but I realized it would be really difficult for students who haven't taken calc of any sort to conceptualize the formulas or even the behaviors of these systems. So I'm going to start off our channel with calculus in physics. I didn't want, as I said before, it'd be hard to conceptualize with E&M. So we're going to be doing the basics in mechanics, because I feel as though all the concepts in mechanics, such as position, velocity, and acceleration, are things that are easily observable in our everyday lives, which means you'll get it. You'll get it very fast. Okay, let's begin. I apologize. This is my actual first... Oh wait, I could just scroll down. It was my first time using this Apple Pen or this iPad, like, in general. So, yeah, we'll see how it goes. Before we start, we have to go over derivatives and integrals. I'm not going to go that in depth with them because this would not be a physics video, it would turn into a calc video. But just for the basics, a derivative is going to be the rate of change. And the way you would write it, for example, if you want to write the rate of change of velocity with respect to time, you would write dv over dt. An integral is going to be the area under a curve. That is going to be written with this really big S. You're going to put the function and then what it's in respect to, right there. A way that I could show this can be obviously through graphs. If you have a graph that looks like this, you take this point, or no, if someone asks you to just find the slope of this entire graph, the slope at this one point, the instantaneous slope at this point, looks something like this, kind of like tangent. Well, it is tangent. And the slope, let's say somewhere here, pretty much looks like the opposite. Excuse my lines. So if you're asked to find the slope of this function, you can't give them an answer. There's an infinite amount of slopes on this line here. An infinite amount of points that correspond to all those slopes. Which means, if someone is asking you to find the derivative of something, at a certain point, you're finding this instantaneous slope at that point. Why does this matter? I will get to that later. Now, for integrals, it's a similar concept. If you're given a graph that looks like this, and someone asks you to take the area under the curve, obviously, if this is 5 and this is 2, you know it's 10 because, base times height. But what happens if you're given a graph that looks something like this again, something really wavy? How would you do that? This area is going to be different than this one. The way an integral works is you actually add up all these infinitesimally small rectangles to get a precise area under this curve. Cool, right? Now let's relate this to the physics that we know and love. The easiest way to initially conceptualize this, I would say, would be with the example of throwing a ball in the air. So you throw it up from a position X, it reaches a height H, and then it comes back down to the same position X. So let's just draw out all the graphs for this. It would be, this is X as in position, and this is time. So it would look something like this. Not perfect, but I'm trying. Oh, wow. Okay. And the velocity time graph would look something like this. And then the acceleration time graph is going to look like this. Well, actually, it should be negative. So I'm just going to act like it's there. To be fair, it does depend on your sign convention, so I'm just going to put it on top here. But just know that you can put it both ways. I'm just, based off of my sign convention, I think it makes more sense to put it here. Ignore that. Now, as we know, V is always going to be the slope of your position time graph. As I said before, how would you find the slope of this function when all these points have different slopes? This whole function does not have the same slope or a uniform slope that we can call the velocity, which means you have to take the derivative at a certain time t if you want to find the velocity there. So if someone asks for the velocity in this scenario at a time t initial, I can say is here, then you would take the derivative at this point. Same thing, I mean, in this case, it does have a uniform slope, so we know we can have a value that we can just keep as this constant acceleration. But when things start getting complicated like this, that's when you really need derivatives, because there's not one slope that applies to the entire function. Now, trying to conceptualize integrals. As we know, x is x, or like the position, or more specifically displacement, is the area under the curve of velocity and time. Now, it's pretty simple if you're given a scenario like this. If you want to find the displacement at this time t1, you can just find this area. It's a simple triangle. It shouldn't be too hard. Once again, base times height, a equals bh. But what if you get something crazy? I'll try and be creative with this quote-unquote crazy graph. Oh, okay, I can't do that. How would you find the area under this? You can be like, oh, I can try and pretend this is a perfect trapezoid. Same with this one. Same with this one. And now things are getting a little crazy with these curves, and it's really not working out. You have to have infinitesimally small trapezoids, and you know what that means? Integral time. So if you want to find the area under this curve, aka your displacement, you need to do the integral of the velocity function with respect to time. Now that we understand this, hopefully, I hope we understand this, once again, if you just want to review, like, if you wanted to find the velocity from acceleration in this scenario, all you have to do is calculate this rectangle up to the point t of interest, the x value t of interest, right? And you would get the velocity at that point, but you can't do that if it looks like this, you know what I mean? That's why you need higher level math. Now that we have gone over how they're all related and how you can use them and also why we use them, there's just some basic formulas that you need to know. I mean, I pretty much said them, but sometimes, ooh, thunder. Sometimes it's nice to have these things in writing. So dx dt is velocity. So rate of change of your x with respect to time is going to be your velocity. X as in position. Now dv dt, I can just write what it is under, is going to be your acceleration. Now the opposite, since these functions actually go both ways, so the opposites are going to be the integrals. So x is the integral of the velocity time function, and velocity, these should be functions, sorry, is the integral of the acceleration function. This all looks pretty cool, but I think we should just practice some really basic examples, and that will be all for this video. Now, if you're given a velocity function, this should be t squared plus 3t. Now, if you wanted to find the displacement, you would integrate this function. So x of t equals the integral of t squared plus 3t dt. Hopefully you know basic integration rules. This would turn into t squared over 3 plus 3t squared over 2 plus c. So if you're given specific bounds, you can plug those in. You don't need c. But in this case, you do need c, the constant. If you're trying to find the acceleration, as we know, is going to be dv dt, which means you have to take the derivative of this function instead. So that's t squared plus 3t, which turns into 2t plus 3. So if you're given a specific time t, then you would just plug that in. So say this is supposed to be at time equals 1. That could be, your acceleration is going to be 5 meters per second squared. Yeah. So I hope this all, oh my god, my calc. I hope this all made sense to you. If you have any questions, drop them down in the comments below. Please smash that like button and subscribe and turn that bell icon on so you get notified every time we post. Okay, bye.